So, my name is Michael Kagan. I'm a CTO and co-founder of Mellanox. And Mellanox is the interconnect company. We deliver high-performance network solutions, starting from 10 gig and all the way up to 200 gig per second. We deploy or deliver two types of network technologies. One of them an InfiniBand, and the other one is Ethernet. And I'll talk a little bit about both, and I'll talk about what happens with AI and with the data center. So we started the company in '99, but the first significant appearance on the market was on the top 500 list of 2003. Virginia Tech professor Srinidhi, I can't pronounce his last name, he decided to build supercomputer out of commercially available off-the-shelf components. So he gone pretty much to Toys R Us and bought 1,000 Mac computers powered by PowerPC those days, because that was the fastest computer out there, fastest processor out there. He bought our InfiniBand technology, and his goal was to get to the top 10 supercomputers on the list. He got to be number 3. That was a great win and great proof that you can actually go to the supermarket and buy enough equipment to build a supercomputer. And another interesting point is that accordingly, this supercomputer was much cheaper than other computers around. Both ASCII, Quadrix, and the number 4 were about 10 times or close to 10 times more expensive than this one that costed him to build about $5 million. But that was long history. Since then, Mellanox Mellanox is delivering the high-performance interconnect InfiniBand for quite a while. It became an industry standard. Actually, more than half of the supercomputers on the top 500 list are using our interconnect technology. Half of them are using Ethernet, half of them are using InfiniBand, roughly. And these are the top 3 machines on the list. Two of them, the first two are in the United States, and this one is a Chinese machine. The interesting part about the Chinese machine is that everything there is Chinese. All the component is Chinese, except for the network, which is coming from Mellanox. Now, these are huge computers with a multiple of thousands of compute nodes. The Chinese one is 41,000 nodes, so you can imagine how big this machine is. And they're actually all running the model of new compute model, which is data flow model. As mentioned, this is the way we build the data processor machine in the 21st century. And this machine is actually determined during the training process that mentioned multiple times before. And this process is being used to set up the parameters in each one of these artificial neurons. So the way computers are built today is different. In the 21st century, we took the CPU, which is classical von Neumann machine, mostly from Intel, but from others as well, and you write the program and you make the application, and the application basically becomes the service. In the 21st century, the story is very, very different. Actually, what builds the computer is not the programmer, but the data that builds the computer. And in order to build the computer with the data, you need to move a lot of data through this machine, through this network, to train the network. And you need to get the data from the storage. You need to move the data between these compute elements, which some of them are on the same machine, like emulated on the GPU or accelerators or the CPU. But quite in many cases, this is a very distributed problem, and therefore you need significantly larger networks. And with Mellanox, our vision is that we are not just offloading the CPU. People talk about multiple technologies of CPU offload and how can we make more efficient use of the CPU by offloading stuff from the CPU. What we are looking at is we are looking at making things that are not possible with the traditional networking technologies and traditional way of connecting compute services. And actually one of the things that first time happened, which we made possible with our network and NVIDIA with the GPU, is the first time that machine become better on understanding the images on the ImageNet classification error. It was in 2016 when Baidu put together machine with the NVIDIA GPUs and Mellanox InfiniBand, and then it was the first time when the machine broke the image classification record by the human. So network is important, and the first thing of the network, we talk about the bandwidth, and the bandwidth is really important. What you can see here is the benchmark of training on the synthetic data on relatively small number of GPUs, 32 GPUs, VGG 16. If you go from 10 gigabit to 100 gigabit, you get 7.5x performance boost. So just pure speed is important. That's the way you move the data between the compute elements. That's the way you move the data from the storage to the machine itself. But that's not all. What we are doing, we are making the network as part of the computer itself. So rather than just moving the data between different compute elements, we process the data as it moves through the network. And it's making this machine, this big cluster, not just a collection of compute nodes, be it GPU or CPU, that each one does its own task, but also network. It has a significant role of actually processing data, not just moving data. And we are accelerating this on the multiple levels, starting, of course, with the network framework, network layer, which is everything has to deal with the reliability and transport of load, ability to move the data much more efficiently between the application and the network, like GPU direct technologies and RDMA, remote direct memory access technologies. We invest quite a lot of making network reliable. Shield is the self-healing network technologies that works on our networks, and it makes network recovery from the hardware failure like cable or switch by 3 orders of magnitude faster than on traditional networks. Going up to the communication framework, there is multiple communication frameworks. We started, of course, with the classical MPI HPC stuff. And what we developed this sharp technology that I'll talk about this in a second. And moving forward, we are actually doing some significant application level offloads, making or accelerations, making this logic to be more configurable, running data analytics in the network. So one of the things that I will talk a bit is a SHARP technology. SHARP stays for Scalable Hierarchical Aggregation Protocol. And what we are doing the data operations on the data of aggregation and the reduction as the data moves through the network. This is the schematic representation of a cluster. These are the compute nodes, and these are the switch nodes. Each switch node has this sharp computing elements, which is actually floating point unit that can do data operations. And with the technology that we deliver today with our switches, you can build 3-level factory topology and integrate 128,000 machines. So you can build huge networks of this, and on each one of these nodes you can have processes running. And if we talk about capability machine or capacity machine, then you can have more than one process running there. And these processes need to do some data aggregation and data reduction operations. The simplest example is just synchronization. So they need to get to some stage on the calculation, and only after all of them get to this stage and exchange the data, they can move to the next stage. And they are sending messages to each other to make sure that everybody is there. So on the traditional computing, they actually talk to each other through the network, and network just moves the data. With the Mellanox, what you can do, you can build sharp trees. So instead of sending data to each other, these guys will be sending data to the network, and each switch has its own compute element that will do the aggregation operation. And once this aggregation operation reaches the top of the tree, the results sent to all the leaves. This aggregation operations is more than 10 times faster than it is done on the end nodes. And the first implementation was for the MPI collective operations. And this is what you see here as a result. The bottom line is actually the aggregation operation on the 2,000 nodes in the Coral machine, the #1 machine in the world, the fastest computer in the world that's deployed there. So what you can see, this is our first generation of sharp technology, and doing it with the other different software technologies, it just doesn't scale. At some point, it goes through the roof. And the time here is actually wasted time, because usually the aggregation operation or reduction operation is something that everybody waits till this operation is completed to move to the next stage. So this is the classical MPI operation, but then if you look at the machine training, then there is if you do the network training by distributing the data to different models and training each model on the subset of the data, then you need to do what is called parameter server, or aggregate the training of multiple model instances to a single training set. And what we are actually doing, we're deploying the same sharp technology to implement parameter server within the network. Our first implementation gave off the chute of fairly small machine performance boost of 16%. That was before we actually did some optimizations. And this machine is very small. As you have seen on the previous graphs from the Coral, when you go to the large machines, that's where you get the most of the benefit. So this is about technology, how to do the machine learning with advanced network. But this was sort of thinking about how to do it on the single machine. Now, the neural network technologies or AI technologies are being deployed in the cloud. And then I will talk about the cloud. Do you know when was the first cloud download? Anybody knows? It was about 4,000 years ago when Moses got the scripts in Sinai. So the Passover night is this Friday. We'll talk about this. But when we talk about cloud today, we have some different meaning of the cloud. The cloud is actually the service provider. And the trick in the cloud is not to put the application and put it on some particular piece of hardware and let it run. Like each one of us would have its own power station if we would go to the power with this model, but rather associated the application with the resources that it needs to execute its task. And this association with the resources is critical to implement it in the efficient, both from the consumer perspective, so you have the same look and feel as if you would run on your own machine, but also from the data center owner perspective, so it must be very efficient. So this association means that you actually you can run application on one machine and use the storage or accelerator on the other machine, and therefore you need some sort of intermediate to associate and pull together these resources from different physical places. It is obviously you need a very efficient network, and this is usually called virtualization, and virtualization comes with a toll. If you look at the bare metal machine, it's all yours. You can use all the cores on the machine for yourself. When you go to the virtualization, there is a fairly significant amount of compute power you need to invest in order to make and manage all these resources and pull them together. Fortunately, there is really two parts on this virtualization thing. One is the control path, which is deciding who runs where, and then there is data path, actually, when you move the data and execute. And this data path can be easily, well, not easily, but it can be straightforward way of loaded to the network. And that's what we are doing with our ConnectX adapter family. So if you look at this in this logical components where you have all the data paths actually running in the gates on the adapter, while the control is run on the host machine. So now we have actually new compute tier. Okay, there is a compute tier that didn't exist before. It's infrastructure computing. It's now you need to manage the infrastructure and run the infrastructure. You can offload the infrastructure data path to hardware, but you do need to have some compute power and brain to control and provision it, and this is actually what is all the competitive advantage of cloud providers are, how efficient can they manage it. Now, this architecture gives very cool results in terms of performance. If you, this is the standard test of the OVS is the virtual switch offload. It's being able to deliver network connectivity to the virtual machine. So we can, with this offload technologies, we can run 10 times faster without consuming any CPUs. So very good. And actually, Alibaba and Microsoft and Facebook, they're all using our network adapters in their data centers. But the point is that now we talk about security and the protection of the data center. In the data center, there used to be an opinion that you can protect your data center by putting really good firewall on the periphery. When we talk about the cloud provider has no clue and has no control on what type of software is running on his machine. He actually invites all the guys from the street to run their software on their machines, and obviously you can get the malicious software out there, and once you have malicious software, you can get actually to your infrastructure and break your break to your data center, and you can spy not only after your clients, but after you yourself. And once he takes over of this control path, he actually can do with the data center whatever he wants. Okay, so this is the core issue here is that the same compute domain is used by the victim and by the attacker. I'm not going to go through the long history of security breaches that happened last 30 years, but last year we have seen a new security breaches, which are based on the very way CPUs are designed. So if attacker and the victim use the same compute domain, it is not going to work, and eventually it will be broken. So we at Mellanox come up with the new product line, which is system on a chip, smart NIC, integrating our adapter with some compute power. And this way, actually, this adapter becomes computer in front of the computer. There's a complete isolation, and there are two different compute domains. One is for the application tier and the other one for the infrastructure tier, and they're isolated, and if bad guy gets to the compute server, it will not be able to go out, and actually we have a technology from the NIC to identify that bad software is running on the machine, and machine is compromised, and notify the administrator that something bad happened and he needs to take care. So that's pretty much the conclusion is that besides the compute power, you need to have a very good network solution, and there is a lot of software needs to be run and needs to be developed in order to make it work. And this is the way to build a data center. Somebody talked about the software. I fully agree that silicon components without software are just expensive sand and not more than that. And with that, I'll conclude my talk.